don't stop, make it pop, DJ blow my speakers up tonight. I'ma fight till we see the sunlight. Tick tock on the clock, guess the party don't stop.
Alright, welcome to section 8.2. Today we're going to be talking about radians, and you've probably never heard of radians before, but they are very much connected to the idea of degrees that we were talking about in the last lesson. So today we're going to go from degrees and we're going to change them into radians, because in trigonometry mostly everything is used in radians and not degrees. So we're going to talk about some conversions today, how we can go from degrees that we're kind of used to, because I'm sure you dealt with a lot with degrees in geometry, and transforming them or converting them into radians. That way we can get into a lot of trig so far this semester, because trig deals with radians. So to kind of ease our way into all these conversions between degrees and radians, we're going to talk about just how we can convert from different units. And I just wanted to bring up this idea of metric time. You've probably never heard about this before, but way back in history, actually not way back, okay, maybe a few decades ago, there was a big push to convert our U.S. standard measuring system into a metric system. And you're probably used to metric in your science classes, where you deal with meters and decimeters and centimeters, millimeters, all that metric idea. So instead of using the traditional 24 hours in a day and 60 minutes in each hour and 60 seconds in each minute, if we were to consider using a metric system for our time intervals, it would look something like this, where one day is kind of related to 1 meter, and we would be talking about decidays and centidays and millidays instead of minutes and seconds. So let's try to convert this idea of a 30-minute episode of Gossip Girl, or whatever your favorite television show might be, into centidays. What would 30 minutes that we're used to using be like in terms of centidays, or this metric time? So you're probably used to doing some dimensional analysis from chemistry or your science classes, where we can talk about these conversions. Okay, we can have 30 minutes and easily convert 30 minutes into an hour. So there's a conversion between minutes and hours. For every 1 hour, there's 60 minutes. And notice how we set up that ratio, because you can think about this as 30 minutes over 1. And if we're going to cancel out minutes in terms and leave it in terms of hours, we got to make sure our minute units cancel, meaning we have a minute up top of a fraction and we have a minute in the bottom of a fraction. But now we can convert hours into days, because remember, our goal is to get to centidays. So for every 1 day, there's 24 hours. Again, notice how we're canceling out that hours unit. So if you want to, you can think about canceling them out, because right now we're talking about days. But now we somehow got to convert days into centidays, and that's where this idea comes in. So for every 1 day, we would have centi meaning, oh, probably should have dealt this one right there. Centi meaning 100. So we would have 100, maybe we'll say CDs for centidays. And notice how the days are going to cancel out. So the only unit we have left is centidays. Now all of these conversions are fractions, and to convert, we're going to multiply these conversions together. When we multiply fractions, we can go straight across. So 30 times 1 times 1 times 100 would give us, what, 3,000? And then we have 60 times 24 times 1 times 1. And I believe that would give us 1440. So then we can do this conversion. If we did 3,000 divided by 1440, we get about 2.08 centidays. So if we were to use metric time, we could anticipate 30 minutes being about 2.08 centidays. Alright, so before we dive into some radians, let's just do a quick circle review here. We kind of dealt with circles in the last section when we were talking about degrees, but just as a refresher, circumference, when we're talking about a circle, is if we were to walk around the outer edge of a circle, that would be considered the circumference, or in other words, the perimeter, okay, the distance around an object. And when we're dealing with a circle, we can talk about the radius, okay, the distance from the center of the circle to the edge of a circle. We can also talk about the central angle, okay, maybe we're going to cut an angle out of this circle. Okay, we can label that as theta. And we also have, when we do cut out that central angle, we have this arc that is forming between the piece that we separate, or the chunk that would be missing from the circumference, the distance around the circle. So circumference, hopefully we know a little formula as 2 pi r, or in other words, pi d, where d is the diameter, okay, the entire distance through the center of the circle from edge to edge. But what we can also do is, with this information, is calculate an arc length. Okay, maybe we actually want to calculate, okay, we know the entire distance is their circumference, but maybe we want to actually figure out what is the distance, what is this arc that we are removing. Okay, that would be considered an arc length. Okay, the length of the arc that this particular angle forms from the entire circumference itself. So let's take a look at this section. Maybe we are specifically forming a 60-degree angle in our circle, and our circle has a radius of 8 centimeters. Let's figure out what is this arc length that this angle is forming. So what we can do is first calculate the overall circumference, because we have this information from the radius here. So the overall circumference would be 2 pi times 8, okay, that radius piece. And if we were to multiply that out, we would have 16 pi. Okay, so the entire circumference of this particular circle has a distance of 16 pi centimeters. But we only want to calculate this particular section, or that particular fraction of this circle. So we want to take this overall distance and multiply it by just this fractional piece. So the fractional piece is particularly 60 degrees, but the entire 60 degrees, this little section, is out of the entire circle itself, which is 360 degrees. So if we multiply by this fractional piece we're looking at, we can just get this arc length here that we're trying to find. Well, 60 over 360 is just 1/6. So we're really taking 16 pi times 1/6, which is 16 pi over 6. And if we want to simplify those values, 18 over 6 can simplify into 8 over 3. So just this little section right here, this arc length, instead of being 16 pi, which is the entire distance around, it's really only 8 pi over 3 centimeters. So with this little process here, we can generalize a formula for arc length where we take the circumference, or this 2 pi r piece, and we multiply it by the fractional piece our angle is forming. Okay, so we're going to take our angle, whatever that might be, in this case it was 60, but we're going to divide it out of the entire angle degree measure in a circle, which is 360. Now, in some of the examples you're going to see throughout this lesson, and maybe in your practice examples, might be talking about a variable s. Whenever you see s, that's just talking about the arc length. Okay, so whenever you see the little s, this is what we're specifically talking about, this arc length distance formed by a particular angle measure in our circle. Alright, so now let's start talking about some radians. Radians and degrees are basically the same idea. It's just representing a measurement in a different way. Just like the idea of conversions. We could say 1 day, but you could also say 24 hours. Okay, they mean the exact same thing, they're just represented differently. So instead of representing this angle as 60 degrees, what we're going to do is represent this angle in terms of a radian. And radians are going to usually involve pi in some way, just like the idea of circumference uses pi in some way. So particularly find a radian measure, we're going to take the arc length divided by the radius. Now that arc length meaning s, just like what we did in the last example. So we're going to find some arc lengths and divide it by the radius, and that should give us this angle measure in radians. So just as a little general over here, we're looking at this particular angle, and we're going to focus on the arc length and the radius in order to help us figure out this angle measure in radians. Now notice how this example is exactly the same as the one we did. Okay, before we still have that 60-degree angle and an 8 centimeter radius. And we found the arc length specifically to be 8 pi over 3 centimeters when we simplified. So let's go ahead and label this arc length as 8 pi over 3. Now to help us figure out what this degree is in terms of radians, let's take the arc length, this 8 pi over 3, and divide it by the radius, this value of 8. So it might look a little weird. We have 8 pi over 3 over 8. Okay, but we can simplify this complex fraction, okay? We can think about 8 as 8 over 1, and instead of dividing by a fraction, we can take this numerator and multiply by the reciprocal. So in other words, we have 8 pi over 3 times the reciprocal of 8 over 1, which is just 1 over 8. So when we multiply fractions, we can go straight across. We get 8 pi over 24. But when we simplify 8 over 24, we get 1 pi over 3, or in other words, just pi over 3. So 60 degrees in terms of a radian is pi over 3. Notice how I told you that radians are going to somehow be dealing with pi because they are directly related to the arc length, which is found by using circumference, which also deals with pi. So a lot of the radians we're going to have in this lesson are going to have the symbol pi in them. Don't get frustrated, don't get confused. Okay, pi is just a symbol that represents a number. Okay, 3.14. It's not a variable, it's just a symbol, but it is something that we're not quite used to, but we're going to have to get used to it because trig is all about radians. So let's think about this for a second. 60 degrees is equal to pi over 3 radians, or we're just going to do rad for short. Okay, so 60 degrees is the same as pi over 3. What if we were to cut another 60-degree section out? Okay, well that would be another pi over 3 radians. And what if we were to cut out another 60-degree section? Well, that would be another pi over 3 radians. But 60, 60, and 60 all together give us a straight line, which is 180 degrees. But if we were to do pi over 3 plus pi over 3 plus pi over 3 in terms of radians, that would be 3 pi over 3, which just simplifies to 1. Or in other words, just 1 pi. So we have this easy conversion to use between degrees and radians. 180 degrees is the exact same as just 1 pi radians. So when we talk about these conversions between degrees and radians in this lesson, we're going to use this simple conversion. Just like there's 24 hours in one day, we can say that there's 180 degrees in 1 pi radian. Alright, so let's start to think about some radians here. We just found that there was an easy conversion between degrees and radians, that 180 degrees is equal to 1 radian. So if we start thinking about this circle in terms of a quadrant like we were doing in the last lesson, trying to figure out where these terminal sides would end, or in other words, what quadrant, we can do the same thing for radians, just like we did degrees before. But now let's start thinking about radians in terms of this pi. So normally we start on this x-axis, and hopefully we remember that we travel counterclockwise. So if we were to travel 180 degrees, that would be the same as traveling 1 pi radians. Okay, those are exactly the same thing. They're equivalent. They're equal to each other. But notice how if 90 is half of 180, then the radian measure for 90 degrees would have to be half of pi. Or in other words, pi over 2. Now notice how 270 is, I guess, 3 of these sections. So we would have a half of a pi plus a half of a pi plus another half of a pi going 90, 90, 90. So we would have 3 halves pi. Or in other words, 3 pi over 2. This is like 1 1/2. So you could think about this as, I guess, 0.5 pi. If you want to work in decimals, you could think about this as 1 pi. This would be 1 1/2 pi. And then if we travel another 180 degrees, making a full circle, this would end up being 2 pi. So just like we can represent angles in terms of degrees, we can represent them in radians as well. So let's use radians to help us figure out which quadrant this terminal side would land in when we're dealing with an angle in radians. So let's think about 2 pi over 3. Okay, maybe you can think about it in terms of fractions if you'd like to. Some of us might have to convert these fractions to decimals just to see it a little bit better. But if we were to do that, okay, 2 over 3 simplifies to 0.6 repeating. So maybe we can think about it in terms of decimals. Right here, the 90-degree angle would be 0.5, but 0.66 repeating is a little bit further than that, and 0.6 repeating is not quite 1. So it would land somewhere in here. It looks like it would be in quadrant 2. Now if we try 7 pi over 5, 7 over 5 is about 1.4 pi. So we got to go 1 full pi, so maybe I'll use blue for this one, 1 full pi, and then we got to go 0.4, but notice how that's not quite 0.5. So we're not quite to the other half of our y-axis. We're going to be somewhere right here, ending our terminal side in the third quadrant. All right, let's try this one. Notice how we have a negative. Okay, so negative 1 over 4 is about, or it actually is, 0.25 pi. So we got to go 0.25 in the other direction, or clockwise direction, which is not quite a half. Okay, it's actually half of a half. So we're ending in the fourth quadrant. And last but not least, if we did 19 over 7, it would be about 2.7 pi. So notice how we have to go the full 2 pi. So we're going to go 1 full revolution. And then we got to go 0.7. Well, if I go this far, okay, I only went 0.5. So 0.7 more, maybe somewhere right here, where our terminal side would be, looks like quadrant 2. Alright, so some of you may be able to do this in terms of fractions. If you like thinking in fractions, you're more than welcome to. Others of you might have to convert it into decimals if that helps you see where these terminal sides would end. But the point is, we're going to be dealing with these radians when we talk about trig. So get used to looking at them, either in terms of fractions or in terms of decimals. Alright, last but not least, we're going to talk about how we can convert to radians and how we can convert to degrees, because there is a relationship. We know that there's 180 degrees in 1 pi radian. So there's an easy conversion between the two. Let's use that conversion to help us go from degrees to radians. So you can think about this as 210 degrees over 1, and if we're trying to cancel out degree, that means we have to have a degree in our denominator. And if we're trying to go to radians, that must mean we need a radian in our numerator. That way these guys can cancel out. So we're going to use that 180 degree conversion to help us convert. We know that there's 180 degrees in 1 pi radian. So multiplying these two fractions together, we have 210 times 1 pi, which is just 210 pi. And 1 times 180 is just 180. But what we can do is simplify these numbers. 210 divided by 180 simplifies to 7 over 6, and we still have that value of pi. So notice how our degree symbols canceled, and all we're left with is a unit of radians. So 210 degrees is actually 7 pi over 6 radians. Let's try another one. We have 135 degrees. To cancel out degrees in the numerator, we need a degree in the denominator. And in 180 degrees, we just have 1 pi radians. Multiplying across, we get 135 pi. And multiplying across in the denominator, we get 180. Simplifying those two numbers, we actually get 3 pi over 4 radians. All right, one more. Let's try 88 degrees. What would that look like in terms of a radian? Using our easy conversion of 180 degrees is the same as 1 pi. We can multiply across to get 88 pi over 180. And then simplifying our values, we get 22 pi over 45 radians. All right, so there's an easy conversion. We're using this 180 degrees in 1 pi radians to help us convert from degrees into radians. but we can actually go the other way as well. Let's say we start with some radians, like 3 pi over 4, or even 5/3 pi, or maybe just pi over 9. Okay, we can convert the other way using this easy conversion. But notice how this time we're dealing with a radian in the numerator, or in other words, this pi value in the numerator. So if we're going to try to cancel out pi, cancel out that radian, we need a radian in the denominator. And we know that in 1 pi radian, there's 180 degrees. So now our radians are going to cancel. We'll cancel out those rads. And we're going to multiply straight across. 3 times 180 gives us 540 pi. In the denominator we have 4 pi. But look, take a look at what's going to happen. We can simplify 540 over 4, which is 135, but the pi's are going to cancel out. And all that we're left with in terms of our units is a degree. So 3 pi over 4 radians is actually the same as 135 degrees. This brings me to a good idea. Okay, some of us might not be comfortable, and probably never will be, with looking at these in terms of radians. But what you can do is convert these from radians into degrees, and that might help you figure out the quadrant or where that terminal side might be. So don't be afraid to deal with radians, just convert them to degrees if you're more comfortable with degrees. But again, we're going to be dealing with radians the rest of the year, so just get used to looking at them and using them. All right, let's try another one. We have 5/3 pi radians. Using our conversion, there's 180 degrees in 1 pi radians. Notice how our radians are going to cancel out. So multiplying across, we have 5 times 180, which is 900, and we still have pi. In our denominator, we have 3 times 1 pi, which is just 3 pi. And 900 divided by 3 is 300. And again, notice how the pi's cancel out. So all we're left with is 300 degrees. Last but not least, we got 180 degrees in 1 pi radian. Multiplying across, we get 180 pi over 9 pi. 180 divided by 9 is 20. Pi's cancel, so all we're left with is 20 degrees. Alright, so what I want you to do is try these 3 on your own. Get used to thinking about radians. Okay, so graph this radian measure on a coordinate plane. Maybe find a coterminal angle between 0 and 2 pi. Remember, this is the same as 0 and 360. We just want a radian measure between 0 and 2 pi. And maybe you can find all those coterminal angles if we just kept doing some revolutions where this terminal side would end. So go ahead and try these 3, and I'll be back in a little bit to see how you do.
Okay, next item of business is our weekly progress report. Principal Skinner, how's your transportation project coming?
Oh, excellent. Not only are the trains now running on time, they're running on metric time. Remember this moment, people. 80 past 2 on April 47th. It's the dawn of an enlightened Springfield.
Dear God of England, please let me go. In return, I will spell the word color with a U, and I will use the metric system with every cubic milliliter of blood in my... Oh, I can't do it. It's so stupid.
Alright, so let's check it out. You had to first graph 7 pi over 4 radians, see where that terminal side would end. Now, we can think about this as 7 over 4, and that's just the same thing as 1.75 pi radians. So if we were to draw an angle, okay, 90 degrees is essentially pi over 2, or 0.5. Another 90 is 180, which makes sense because we get a full pi. If we go another 90, okay, we're at 1.5 pi, but we got to go to 1.75, which is just a little bit more, not quite 2 pi, so we're going to end somewhere right there. Now, something you also could have done is maybe you weren't comfortable graphing it in radians. You can convert this radian into a degree, and that might help you graph it a little bit better. If we use our conversion of 180 degrees in 1 pi, we can multiply across. Okay, we get 126 pi over, oh, what is it? Oh, just 4 pi. And 1,260 divided by 4 is 315 the pi's cancel, so it's really 315 degrees. And notice how if we think about degrees, we got 90 degrees, we got 180, we got 270. We're not quite 360, so we're just a little bit more somewhere right there. All right, so let's go into the next one. Name a coterminal angle specifically between 0 and 2 pi. Now 2 pi in terms of radians is 1 full revolution. So we want to take this angle and add 1 full revolution to it, or in other words 2 pi, and see where that coterminal angle might be. Now in order to do this, we kind of got to get a common denominator because we're adding fractions. So to turn this 1 into a denominator of 6, let's multiply the top and the bottom by 6. So we're really left with 12 pi over 6 plus this negative 11 pi over 6. Now that we have a common denominator, we can add the tops. Negative 11 plus 12 is 1. So we're left with 1 pi over 6. And notice how 1 over 6 is in between 0 and 2. So there's our coterminal angle between 0 and 2 pi. Maybe we can name all the coterminal angles. So notice how in this one we're in the negative direction. We want to go that entire way. So we're going, it looks like 180 degrees, which is essentially pi, but we got to figure out what is this other piece, what is this section in here that we got to add on to it to get our entire degree. So we got to use this pi over 6, this other piece, to help us figure out this missing one. And if you just think about this little section right there is 90 degrees, but remember 90 degrees is the same as pi over 2. So if we take pi over 2, which is the whole angle, the whole degree, or not degree, the whole radian, I guess, and we subtract pi over 6, this piece we know, we should get this missing piece. Again, we got to get a common denominator, so maybe we'll multiply this one by 6, or by 3. So we're left with 3 pi over 6 minus pi over 6, which is 2 pi over 6, or in other words, pi over 3. Okay, just 1 pi over 3. So that's what this guy is. We got pi over 3. But we go a full pi and then another pi over 3. So we got to take pi plus this pi over 3 we found to get that entire angle. Again, common denominator, so we got to multiply by 3. 3 pi over 3 plus pi over 3 is 4 pi over 3. All right, so that's this whole angle from our initial side all the way over to our terminal side. We go 4 pi over 3 radians, but we're going in the negative direction, so we got to make sure it's negative. And if we want all coterminal angles, we got to add on that piece of how many revolutions we actually want to do. So 1 full revolution in terms of radians is pi over 2. Let's not forget that value of n for how many revolutions we actually want to do. So in terms of our final answer, after all said and done, we have negative 4 pi over 3 plus 2 pi n. Hopefully we did really well with these. Good luck on the practice and the application, and most of all that mastery check, and I'll see you guys later.